Now that we have a definition of what an equilibrium value is, and we've kind of seen a numeric example, we'd like to come up with a way to actually calculate analytically the equilibrium value for a given dynamical system. And the method that we're going to use to do that really comes directly from our definition here, right? The definition says that A sub k is equal to A, this equilibrium value, for every value of k. In other words, A sub 0 equals A sub 1 equals A sub 2 equals, and so on, up to A sub k equals A sub k plus 1, and continuing on forever. This part right here is the bit that we're going to actually use to find an equilibrium value. All right, so hold on to that, and we'll go on to the next slide and look at a specific system. All right, this is the annuity example that we looked at in the previous lecture. Remember, an annuity is an investment where you make an initial investment, and every period, every month, year, or whatever it equals, it earns interest, 2% in this case. And also every period you take a fixed amount out. And in my example here, it's $1,000. So what I want to do is I want to find the equilibrium value of this dynamical system, right? In other words, in practical terms, I want to find the initial investment where the principal, the amount of the account stays constant forever. The amount of interest that I earn exactly equals that $1,000 that I took out. Right? And remember what we said on the previous slide, right? We said if we're looking at a stable system, one that has reached an equilibrium value, then A sub k plus 1 equals A sub k. All right, here's how I'm going to find this value. A sub k plus 1 is equal to this. So I'm going to put this into my equation here. This becomes 1.02 A sub k minus 1,000 equals A sub k. You look at what I've done now, right? I've reduced this down to an equation with one variable. I can solve this. Right, let's move the A sub k over from the right side. 0.02 A sub k equals 1,000. And if we divide both sides by 0.02, we get A sub k equals 1,000 divided by 0.02, which is 50,000. And that is exactly the value we saw in the last lecture where we approached the problem numerically. Right, and remember, we were searching for the initial investment, right, and that's A sub 0. But if this is the equilibrium value, then A sub k is equal to A sub 0 for every value of k, right? So what I have shown here is that A sub 0, the initial investment required to have a stable system, is $50,000. All right, so let's take a look at a more complicated example. Right, this is our the logistic equation that we came up with a couple of lectures back, and I want to answer the same question here. Right, what is the equilibrium value for this system? Well, I'm going to approach it exactly the same way. I'm looking for a value such that P sub m plus 1 is equal to P sub n. And I know what P sub m plus 1 is, so I'm just going to drop that in here. P sub n plus 0.008, that's an 8. P sub n, 800 minus equals P sub n. And now we're in the same situation, right? I'm down to an equation with only one variable in it. It's not a linear equation anymore, right? It's going to end up being if you're kind of looking ahead, it's going to end up being a quadratic equation, but that's okay, right? We can work with this, right? So let's kind of walk through the steps here. We'll distribute into the parentheses P sub n equals 0.008 times 800. This is, whoops, not equals, P sub n plus 0.64 P sub n minus 0.0008 P sub n squared equals P sub n. You see this is actually going to coming out a little nice here. These P sub n's are going to cancel, and I'm left with 0.64 P sub n minus that decimal Pn squared equals 0. And now I can solve this by factoring, right? If I factor out P sub n, I get P sub n times 0.64 minus 0.008 P sub n equals 0. And then I set the factors equal to 0. So I'm going to get two equilibrium values here. P sub n equals 0. And let's see, what do I get from this second factor? I get 0.0008 P sub n equals 0.64, and then divide both sides by what? By 0.0008, and you get 800. Right. So there are my two equilibrium values. We can kind of check these real quick, right? If I put 0 in here into my formula, let me write it over here. Pm plus 1, Pn plus this thing here, right? If I put 0 in there for P sub n, P sub n equals 0 will give me P sub n plus 1 is 0 plus, I'm going to put 0 in there, and that whole factor is going to become 0. So yeah, it worked, right? P sub n plus 1 does equal 0 for every value of n. And we can do it again for 800, right? Pn equals 800 gives me Pm plus 1 equals 800 plus, and now when I put 800 in there, that factor becomes 0, so that whole term is 0. And yeah, look at that, it worked, right? P sub n is equal to 800. It is constant for every value of n. All right, so let's see if we can talk about a general solution here, right? Suppose I have a linear difference equation, right? I have a difference equation where the formula here is a linear expression, right? Can I come up with a formula for the equilibrium value of this system? Well, yeah, I can, right? We know how to do this now, right? I'm starting off with an plus 1 equals a sub n. And I'm going to put the formula here in r a sub n plus c equals a sub n. We're going to kind of move things around, right? C equals a sub n minus r a sub n. You factor that a sub n out and divide, and we get a sub n equals c over 1 minus r. So it's nice. We can come with a formula, right? Now, anytime we have a dynamical system that is modeled with a linear equation, we can kind of jump right to the answer. But I want to emphasize, right? This only works for a linear system, right? For something where the difference equation is more complicated, you have to go back to our method. We could maybe try to do this for more complex systems, nonlinear systems. you're not going to have a whole lot of luck. Nonlinear systems, even what look like relatively simple nonlinear systems, tend to be much messier to deal with than linear systems are. Okay, so what's next? Well, now we've got a pretty good idea of how we come up with these models and some of the things that we can do with these models. Right, so our next step is going to kind of be to take this to its almost to its conclusion. We're going to see how in some cases, again, we're going to do this with a linear system because linear systems are generally pretty well behaved. We're going to see how we can go from a difference equation, which remember is iterative. To find a sub 100, we have to know a sub 99. To find that, we have to know a sub 98 and 97 and so on. That can be a little problematic if we need to find a for a large value of n. So what we're going to do is we're going to look at how, at least with a linear system, we can take our difference equation and convert it into the kind of more general formula that you're used to, one that only depends on n rather than a sub n.